Okay, let's start. Thanks, welcome everybody, and thanks for coming here today. So today we have the pleasure of 1 hour special talk on gamma ray astronomy by our own Wystan Benbow. Not that it needs a lot of introduction, but let me just give some basic info. So Wystan had his PhD at UC Santa Cruz, working on Milagro observations. He was then working on HESS, and then he came at the CfA. He was, and he is currently director of the VERITAS observatory, and he's also been appointed recently the leader of the SAO program office for CTAO, which is the gamma ray facility, the most important gamma ray facility for the future. So today is going to talk us about the very high energy gamma ray astrophysics evolving from VERITAS to CTAO observatory. So we are going to do one step backward to 2 steps forward in the future. So please go ahead.
All right. Thank you for the introduction. Yeah, so as Rodrigo said, I'm going to talk a little bit about VERITAS, which is the most powerful gamma ray observatory in the world right now, but also the transition to CTAO, which is the next generation facility that's going to start taking scientific data in about a year or two. So I was going to highlight a little bit about what we're doing with VERITAS specifically here at SAO, because there's so many results, and then talk about the opportunities and how people might get involved with CTAO alongside my group. So let's start with gamma ray, ground-based gamma ray astronomy. This is when you talk about this, what do you mean? Well, you mean TeV gamma ray astronomy. That's 1 with 12 zeros followed behind it. So it's the highest energy astronomy you basically can do. And it's not something you can do with a satellite. You just simply can't fly a bird big enough to detect the low fluxes of gamma rays at these energies. So you have to do something kind of funny, and it's called the atmospheric Cherenkov technique. And the reason is that TeV gamma rays, the atmosphere is opaque to these things. They come and they hit the upper atmosphere and they create a collision, a particle cascade, which you can see off there to the right. And this gamma ray shower comes propagating through the atmosphere, and as the particles themselves are moving faster than the speed of light in air, they give off radiation called Cherenkov light, which illuminates a pool on the ground or a circle on the ground. And you can put telescopes within this circle to detect the gamma ray. If you put multiple telescopes within this circle, you can then have multiple views of the gamma ray shower of a Cherenkov light therefrom, and you can start reconstructing this to do gamma ray astronomy. This is a technique that was pioneered by SAO scientists at the Whipple Observatory, and the idea here is that even though you need to have a detector that's square kilometer size to effectively do this, you can actually, because you can put just a few smaller telescopes within this light pool, you can get away with very small physical instrumentation to get a square kilometer size. So let's start a little bit about the evolution of very high energy gamma ray physics from the early days. It's had a very humble beginning in 1953 in Dublin. This is minding the era of particle physics, where particle physics and the accelerators were literally done from the sky. People studied muons to find new particles. And in 1953, they decided, let's just see if we can see Cherenkov radiation. So they instrumented a photomultiplier tube in a trash can. Okay, and they went out there and operated at night. And lo and behold, they detected Cherenkov flashes. So this is a great thing. I actually had the privilege of working in the lab in there at UCD. I wrote a Nature paper in the lab where this effort was done. And so that was really quite a bit of fun. I'm out there. And so from this early days, they eventually evolved to a slightly higher level of instrumentation, where they were basically using surplus World War II searchlights in Crimea, or old anti-aircraft gun turrets where they put mirrors on them and put photomultiplier tubes in there. And you would point at a celestial object and do a drift scan, and you try to see if you would get an increase in Cherenkov radiation as these things moved across. So obviously very crude beginnings, but nonetheless, where we all started. This project here in Ireland is where my predecessor, Trevor Weeks, did his PhD thesis. Okay, and eventually moved on to SAO to come here to do the next step. So we've been doing gamma ray astronomy here at SAO for about 60 years. The first instruments had a very humble beginning. It was 2 World War II searchlights over there. They were driven out into the wilds near Amato, Arizona, in the Santa Rita Mountains. Okay, and again, drift scans with stopwatches, photomultiplier tubes. But really, Trevor went out there led by Giovanni Fazio, to build the Whipple 10-meter telescope, which was dedicated in October of 1968. The picture I think is classic. I love that jacket with the stripes and things like this. You just don't see things like this anymore in this era of everything is all black or charcoal. So I really, really think this. And this was actually the very first telescope on the mountain at the Whipple Observatory, which wasn't called Whipple Observatory then. And the really interesting thing I find about this is that most of the money that went to build this telescope actually went to build the road going up the mountain that actually enabled the whole facility in the first place. But this was a fairly crude telescope. Yes, it is a 10-meter telescope, and it's an optical telescope. But if you look at the camera up there, you see two photomultiplier tubes. There was one that was on source and one that was a little bit off source to do the background. And so once again, you point at something, you'd measure the Cherenkov light with your stopwatch and a scaler, and you'd measure off source and you'd try to see something. Well, lo and behold, this didn't work so well. Okay, so it took them about 20 years, and I'll explain what happened over those 20 years. But after about 20 years of struggle, they detected the first galactic source, which was the Crab Nebula in 1989, and then the first extragalactic source in 1992, which was Markarian 421. And so this led, through some evolution to eventually have VERITAS, which was dedicated in April of 2007, and it's been running for the past 20 years since. So what enabled modern gamma ray astrophysics? And one is the advent of imaging Cherenkov cameras. And so you can see what they started was with a 1 pixel, but eventually they moved to a 37 pixel camera. The idea is that the images in these Cherenkov cameras have an elliptical shape. And if you can characterize this elliptical shape, you can then start to discriminate from the background, which outnumbers things by more than 10,000 to 1 per unit of energy. And so over time, the cameras grew, from 100 pixels to 300 pixels to 500 pixels. This one right here is widely considered the best camera of that era, the 300 pixel camera. And this doesn't sound all that impressive. And, given my iPhone has, 10 million pixels or something like that, the reason it is impressive is because you're effectively taking 1 billion pictures a second to do this. And yes, you stitch them together in some sort of integration, but it's the fast electronics that makes this possible. The other thing that made things possible was the advent of stereoscopia. I remember I said you could put a bunch of telescopes in the light pool, and so Hagrid did this in the 1990s in the Canary Islands, and you can see a couple of their 4-meter telescopes right there, or they had a much smaller camera, again pixelated, but they found that 5 4-meter telescopes did as well as 1 10-meter telescope with a larger camera. And so, of course, this meant that, why don't we just have bigger telescopes with lots of pixels and lots of them, and that is how you get to modern astrophysics. And then, of course, after we built something like that, we started having advanced computing methods, and you can imagine all kinds of neural networks and boosted decision trees and random forests and everything that all of our AI friends love to use. And that's really meant the later advances, this past decade or so. So there's been an explosive growth in the field. When I finished my PhD in 2002, there were about 10 VHE gamma ray sources, and the redshift horizon was about 0.1. Now there are about 320 sources going out to a redshift of 1. And I was working on something this morning that might have broken that 1.0 barrier, so hopefully that goes. There's now about 10 source classes, and we have 6 major facilities meeting something on the scale of $20 million or larger operating. Okay, so you can see the catalog right there. This is a galactic projection. You can see they clustered along the galactic plane. There's lots of supernova remnants and pulsars and pulsar wind nebula and binaries. And then the red dots out there, which are different flavor sources, are mostly active galaxies. And so you can see this thing is growing, and it tracks very much like X-ray, satellite-based gamma ray, and this is ground-based gamma ray. You can see that you start at your humble beginning, your first source, and it takes you a few years to get to 10, and then a few more years to get to 100, and then 1,000. You see the same thing with satellite-based gamma ray. This is when I was in graduate school, where they were at like 60, and now they're at 5,000. Okay, and then when I started in the field, we were at 3, and we got up to about 50 when I came here, and now we're at 300. So there's an explosive growth, and with the next generation facility that you'll hear about, we're going to enter the era of thousands. So what is VERITAS? Well, VERITAS is a 3rd generation VHE facility. It's 4 Cherenkov, 12-meter diameter Cherenkov telescopes on a square of about 85 meters side. It operates from September through July every year. We shut down for summer monsoons in Arizona. And we do these very high energy gamma ray studies, and we've been doing them for 19 years now. We're going on our 20th season next year. Some of our, just to give you a feel for what our parameters are, our angular resolution is about 0.08 degrees. The Crab Nebula is the brightest DC source in the sky, and our sensitivity says that something about 1% of that we see in a little bit under 25 hours, just to give you a scale for how fast we see things. If you look a little bit at the hardware, you can see the telescopes are indeed large. There's a person standing next to the telescope. You have the telescope itself. This is effectively a glorified missile launcher positioner right there. You have a camera up there at the focus. It's about 1.8 meters across. A bunch of wires come down into an electronics trailer, which goes to a central control building. You see the mirror itself. It's a 12-meter surface. It's a spherical surface, but it's made up of 350 individual facets, which focus the light. And so this allows you to build it very cheaply. So it's about $350,000 for a 12-meter mirror surface, as opposed to probably something on a scale of multiple millions to build something out of solid glass. That would also be quite heavy. The instrumentation itself is photomultiplier tubes. There's 500 pixels here in this camera. Okay, and again, remember to focus on the billion pictures a second, not the so few pixels. So where does VERITAS stand in the global context? So right now, what you see here is energy versus flux sensitivity. This is VERITAS right here. We're the most sensitive thing going right now. Hess is basically right with us. MAGIC is another facility that's a little bit less sensitive than us. There's something called LASO up in Tibet, which is maybe a bit better at higher energies, but in our regime, we're the best. So we're the most sensitive thing in the world, but there's something called CTAO, which is being built right now. And you can see the northern sensitivity and the southern sensitivity right there. And CTAO is coming online, and it's expected that its sensitivity will surpass VERITAS sometime late next year. And so operations of VERITAS are funded through September of this year. I have a proposal pending for a 20th and potentially final season. I'm going to put that in quotes because the ground always moves on me next year. So what has VERITAS done? Well, let's start with the basics. My job is to lead the project office and operations. So we have 21,000 hours of data. I want to give a shout out to Bill Hanlon, who's my site manager. He does cosmic ray research, which I don't have time to talk about today, but he really helps me get this done. He's a PhD scientist. And what you can see here are the raw observation hours, VERITAS per year. We've averaged about 1,200 hours per year since 2012, and we always exceed our technical performance metrics. So this machine runs really well despite being nearly 20 years old. We had a dip here in 2020. I think we all remember getting locked in our homes for a few months. So we missed that year, which is hence the asterisk. But with VERITAS, 95% of our data have all 4 telescopes operational. These machines are really fussy. MAGIC has only 2 telescopes, and it's only 88% of the time their 2 telescopes are operational. So for us to be running this well is quite an accomplishment, and we lose very little time to technical issues. Another thing that's interesting about this is that you see this is all time. This is what we call dark time. When we started in 07, we couldn't take Cherenkov data during moonlight. And we pioneered that in 07. Take it when the moon was, say, I don't know, up to 33% illuminated. And this added 16% to our data yields. And then we came up with a way to operate during the full moon. This added another 17% to our data yield. So we really are trying to push this machine as far as you can go. Recalling it was designed to run for 10 years. We're getting, roughly 30% more data than expected. So we're really pushing this machine. Wow. So what does VERITAS look like today? Well, here you see VERITAS. You see in the background a red telescope. This is a CTAO prototype at the Whipple Observatory. We operate both instruments to do gamma ray astrophysics, and this is helped by Alicia Cromie, who's another PhD scientist. She helps us lead our observing teams, and she does supernova remnant research, which I don't have time to discuss today as well. So what do we see with VERITAS? Well, I took this picture in 2014 when I was out there, and yes, there's a double rainbow, and it actually ended right there. And I can tell you there's no pots of gold at the end of a rainbow. I've checked because I could have really used the funding. But we see other things as well. So you look at the VERITAS source catalog. We're up to 78 sources from 8 different classes. The different color objects are different source classes. And we're really active. This has increased by 25% in just the past 3 years. So it's 20 years old, but we're still finding new things. We've put out 153 papers and 88 PhD theses. We just had one finished yesterday. So another big accomplishment. And 11 papers just came out in the past 12 months and 7 PhDs in the past 12 months. So this thing's really doing a lot of good science still. But if you look at this primarily, if you look at the map, this is again a galactic Coordinates with blue is what we see. It's about 70% AGN, and that is what the SAO group focuses on. Specifically, we focus on AGN catalog efforts. So VERITAS has looked at about 250 AGN. We've seen about 51 of these, and they're primarily blazars. There's like 3 or 4 radio galaxies that we've detected, but it's basically AGN with jets, where the jets are pointed right down the line of sight to us. Okay, and we lead both the discovery program and the catalog program for VERITAS. We've discovered more than 20 new AGN, and we've generated a comprehensive set of limits for about 200 objects. And when I say comprehensive set of limits, what do I mean? Well, if you look at an AGN, this is a distribution of power versus energy, and it has 2 bumps. And most non-thermal sources do. Okay, and the thing that happens here is that this bump right here goes up and down. It can move left or right. Okay, and so what we do is we say, okay, we're going to look at a subset of AGN where the bump is at least this bright. We're going to look at all of those. Okay, and we're going to look at all of those where the peak is above, right about here. So not ones that are down here, but above here and up here. And we're going to look at every single one, because those are the ones you see at TV, and we're going to find out which ones we see. We're also going to look at all the hard spectrum Fermi lat sources. This is the Fermi spectrum right here. And anything where it's rising or flat or maybe just a little bit turned over, because this peak also moves, we're going to look at all of those. So what we've done is we've surveyed all the sky for everything you could possibly see, and that's what we're going to try to detect. And then, of course, we want to do science, so we're going to try to model these things. So we look regularly at every northern VHE-AGN. We collaborate with Fermi, which is an all-sky monitor. We have swift pointings simultaneous with our data for all of these observations. We have FLW48 and radio partners that give us these things, but ultimately allow us to model this. And my postdoc, Matteo Cerruti, in 2014, he modeled this emission. It's called an SSC model, which I won't go into. I think many of you have heard of it. But the interesting thing here is that when you do this model, it used to be these were very degenerate back in the days. Nowadays, the precision of these observations are so strong that the model parameters come back to within a factor of 2 when you can make error bars for it. And now this is 10 years ago, and obviously the state of things has evolved. You have more VERITAS data, you have more Fermi data, you have new star, things like this. So I just want to show a few of the recent discoveries. Okay, so these are what are called HBLs, where the synchrotron peak, that lower level peak, is at 10 to 16 hertz or above, 15 hertz or above. They're at higher redshift, so redshift of 0.3. Sometimes they're unknown, sometimes they're variable in Fermi lat, sometimes they're not. They're always hard spectrum. Okay, this figure of merit is what the ratio of their synchrotron flux is to the lowest detected source. So, modestly bright. But what you can see is that all these detections are starting to come in at about 50 or 60 hours. And the reason is that when we first did the survey, we looked at everything for 10 hours. Then we decided, okay, now we're done. We're going to go follow up and find all the things that are really hard to see. And so that's what we're announcing right now with all these things that are hard to see. They're all right at the sensitivity limit of a detector, and they're all fairly soft spectrum. Okay, just showing you another set. This is 2 more that we've seen. This is one that came in this morning. This is a plot we actually put out last September, but I have a much more significant thing. And the lower limit on this redshift is 0.48. There's stuff from SDSS, which you may not want to believe, but it says it's over 1. So we're trying to figure out how far away it is to see if we've actually broken the redshift horizon. But as you can see, they're getting less and less bright as we work through the catalog, and getting much, much more soft as we go through. Okay, so that's a little bit of stamp collecting in some sense, building up the catalog. But I wanted to talk about my favorite project, which is 3C273. I've been working on this for almost 25 years. It predates VERITAS, okay, and it's sort of my career goal, if you will. It is the original quasar, okay? I've been to IAU symposium where we talk for an hour just about the discovery of 3C273. Okay, it's located in the direction of Virgo. It's about 2 billion light years away, and it's one of the most well-studied astrophysical objects. There's about 400 swift exposures, just to give you an idea of how well-studied it is. And you can see that it has a jet that's resolved on all scales. You have, micro-arc-second scales from ALMA, you have milli-arc-second scales from HST, and of course you have the famous Chandra image as well. And one of the things about Chandra that's very interesting is that this jet has an anomalously hard X-ray spectrum. And I'm going to come back to that in the story. It's a variable soft spectrum Fermi lat source, like many quasars. It doesn't make it particularly exciting, But the one thing that I will say is that it's a very unlikely TeV source. If you take the Fermi spectrum and extrapolate it to the VERITAS energy band, the flux is much, much less than 1/100% of the Crab. So you do not expect to see it. Now, of course, you might say you see it during the flare, and there have been a few major flares. There's one in 2009, one in 2016, and one in 2024 that we could have observed. But I'm going to tell you, this is not why we might have seen it. So this, I'm announcing, and I mentioned this at the ICRC last year, the VHE discovery of 3C273. Okay, this is going to go into Nature Physics sometime a little bit later this year. What you can see is we have a 350-hour data set over the past 17 years. Okay, you go through and you select it for absolute quality, and you come down to about 230 hours. You see we have 5 sigma detection as sort of this gold standard. We just get there. Okay, and we've worked on this in a variety of ways. So you have to account for some statistical trials. So it comes in about 4.9. It's confirmed by independent analysis. But what you can see from the flux is 0.2% of Crab. This is the weakest TeV source ever measured. The flux that you see right here is the light curve. These are limits when the significance is too small. If you fit that to a constant, it is constant. There's constant flux coming from this VHE source within the realm of our very weak statistics, of course. But that's not why it's interesting. We see it, that's great, it's always kind of fun. Why is this interesting? Well, what you see here is the Fermi lat spectrum. Remember I told you it was curved, it pulls over, and you don't expect to see it, VERITAS energy. This is the VERITAS spectrum you see. There's a clear disconnect right here. The VERITAS spectrum is incompatible with Fermi. Well, you can say, well, maybe it's variability. So what do? I can take the Fermi data and say, what is simultaneous with the VERITAS data taking, strictly simultaneous, make that spectrum, and you see this here, and you see it's still incompatible. And then, of course, the thing is that, this is called the extragalactic background light, which feeds gamma ray photons, okay, and that absorbs things, and so the spectrum would actually have to get cut off, but you see it's much, much worse. So it's about 5 sigma, basically we're not expecting to see something, we do see something, so it's incompatible. But what's really interesting about this is if you take this extragalactic background light out and say, what does this look like intrinsically at the source? Once again, you see this Fermi spectrum, which is curved and rolling over, but if you take the extragalactic background light out of VERITAS, then you see a rising spectrum. This indicates a new emission component in 3C273, something that somebody hasn't seen before in AGN. So I put this out at the ICRC last summer, and almost immediately somebody put a paper on the archive on a Fermi AGN saying, hey, I got a hint of something like this too. Maybe there's something going on that's similar. And now I think there's a third one that's coming out. So it looks like we may have a population of multi-component AGN coming out. Okay, but is this variability? I've tried to tell you it's not, but let's prove it. So what you see up here is the Fermi light curve. You see it's on probably monthly bins or something like this. You see it's moving up and down, and there's a big flare in 2009. But we don't have any data during this. In fact, most of our data starts here and goes all the way up to about there. Okay, when it's very low. So curve, okay, and you basically come up with, okay, there's a few bright periods in a low state. And so what you can do is you can say, what does VERITAS see during the low state? What does VERITAS see during the bright period? And you can see right here that we see, within low statistics, the same signal in both epochs. So obviously, if it's, steady emission, it shouldn't vary. And if it were all coming in when it was bright, it would be bright when it's, high and not when it's low. And that's not the case. In any case, you see that this is the low state of Fermi. This is the high state of Fermi. This is the highest single state ever seen from Fermi. And you can see that none of these Fermi pairs are compatible. So there's obviously something different going on. Well, what is different going on? Well, you can do some SCD modeling. This is conceptual. This is not, I'm not fitting anything. I'm literally just gonna take this model, throw some parameters in and see if I can reproduce them. Okay. So you take the SSC model, this is the spherical cow of AGN modeling, throw it on there, and you can see the archival data, the Fermi data, the VERITAS data, and what do you see right away? It does okay. Maybe misses the radio data a bit, misses the blue bump a bit, and it certainly misses VERITAS by a lot. Okay, everybody knows that, FSRQs, you have to use something called an external component in addition to SSC. And you do that with this, and you see, oh, it does a little bit better, but it still misses VERITAS by a lot. And you can start playing around with this model quite a bit, throw in some extreme parameters, and maybe boost the second order SSC component to this, and you can push that up. But you start to overshoot Fermi, and you still miss VERITAS. And so basically, there's nothing you can do to model this in any sort of reasonable SSC way. So what is this? Well, I think it is inverse Compton scattering off of this cosmic microwave background. What you see down here, up there is what's coming from the AGN core. This is the integrated emission from the AGN jets. Everybody believes this is synchrotron emission, but this emission right here is this anomalously hard X-ray spectrum that was seen by Chandra. And for about 20 years, people have been arguing whether that is another synchrotron component or whether it's inverse Compton off of CMB for this. And what this shows is if this is synchrotron right here, it would naturally have inverse Compton scattering, and you get reflected bumps here and here. And the fact that we see VERITAS is saying that this must be synchrotron, this must be ICCMB, and we have now detected this signature, which sort of answers this 20-year-old jet mystery for us. And you can get a variety of parameters out of this. So that's the big result. Took us 350 hours. A lot of hard work. The interesting thing is that CTAO, which I'm going to talk about in a little bit, it can make this study in about 3 hours, right? There's a population of these things that should be excellent CTAO targets. So really CTAO should be able to hit this really hard and say definitively when I'm stretching VERITAS as hard as one can possibly stretch it. What else are we doing? Well, we're making the first AGN catalog. I'm an astronomer. I'm supposed to show constellations. So what you see here are red dots with all the VERITAS AGN detections. It's the constellations. We see our first constellation that we made. These are all AGN that fall in a single field of view. That's very fun. And this is being led by my postdoc Juan, who's over in the OIR corridor if you want to speak to him. And so what we're trying to do is we're trying to create standardized results for all of the AGN. What we see is we've looked at 75 of them, about 6,400 hours worth of data. This right here is what we call a deep exposure. This is a relatively deep exposure. That's early data. And you can see that for 75% of the TVAGN, we have a deep exposure. Okay. So we're going to generate flux, spectral variability studies, position and extension information. And as we're going through this data, systematically analyzing these very large data sets, 5 that we've just released already. New detections for VERITAS are things seen by other people, just sitting in our data waiting to be pulled out and released to the public. They're all, relatively weak, which is what you would expect. There's more of these to come. We're working on topping up the things that are like 3 or 4 standard deviations, but we're really trying to give a systematic overview of all the TeV-AGN. What do some of the catalog results look like? Well, you see the sky map, you see a positional fit, you see the contours on where that positional fit is, how it compares to the AGN location. Maybe it could differ. You try to get extension in case there's something about the intergalactic magnetic fields. You measure a photon spectrum, you make light curves, and you quantify the variability. And this is a quasar that we saw in just one single year. You see that we don't see it, we do see it in this year. Superimpose the Fermi light curve in the background. And you can see that there was a big Fermi flare, and that's why we saw it. And of course, those were triggered observations. But, so this is the type of thing we're trying to put in a systematic way for the first time for a TeV catalog. Okay, what else are we doing? So Claire is my graduate student. And in 2022, we observed a flare from BLAC. The red is a Fermi light curve, is gamma ray. You see that sometime in October, there was a big spike in the Fermi emission from this object, and we started following up on it. And normally we see this thing for about a half hour after one of these flares, and then it just disappears, goes and hides away. But what ended up happening in our follow-up observations was, say, a month or so later, we detected still persistent emission from it. Okay, so we decided to, take this period, this delayed flare, if you will, from it, this long duration flare, try to, do a multi-wavelength modeling. We got some new star data. There's some SWIFT data. Here's some optical data, and we decided to try to model this. What is going on with this object BLAC, the iconic blazar, if you will? Well, BLAC, which you can see right here, its synchrotron peak is somewhere around 10 to 14 hertz. Okay, And that means it's not an HBL like all the TV lasers, it's called an IBL, something in between the population that Fermi generally sees well and what we see well. Okay, and this HBLs, these high peaked objects, tend to be SSC models. This top model here, the things that are like FSRQs tend to be SSC plus EC. So what is this intermediate population? And so what we found was that if you fit this to the SSC plus EC, like the lower peaked objects, it fits really well with the 7 sigma preference. Whereas if you're trying to use a thing like HBLs, it doesn't work very well at all. Okay, so that's during the flare, but what about the low state? Claire is finishing up her thesis. We measured the low state. The SEV model, a final one pending. I didn't feel quite comfortable showing it right now, but what I can tell you is that the low state is different from the high state. That is more like an HBM. So very interesting stuff. So the other things before I hit over to CTA is the origin of cosmic rays. Okay. This is the Nature paper I referenced earlier that I wrote in that lab. We originally observed M82 in 2008, 2009 for 175 hours. We went all in. We saw 5 standard deviations, 91 gamma rays in 137 hours a day. You gotta have patience in this field. Really a lot. If you do the work on this, you can propagate this through a bunch of models, and it tells you that the cosmic ray density of M82 is about 500 times that from the Milky Way. So why does this affect supernova origin of cosmic rays? Well, we know that there's a lot of star birth and starburst galaxies, hence star death, which is a supernova. So if you have a lot of supernova in M82 and there's a lot of gas in there, if supernova are a primary source of cosmic rays, this cosmic ray density that comes out of there would require a 10 to 30 times higher supernova rate in M82, and that is actually what is observed. So that we see TV gamma rays because these cosmic rays interact with the gas to create gamma rays. The level we see requires, basically that supernova are the source of cosmic rays. So obviously we wanted to dig in a little bit deeper about this, and we finished this just last year, a 360-hour exposure where we got ourselves up to 135 gamma rays. We hardened up our cuts to really get precise. But we have this nice spectrum you see right here compared to what we put out in the Nature paper years ago. And this is led by one of my staff members out of VERITAS Law, and we model this. And if you do the modeling, you clearly see that it prefers a hadronic scenario for the acceleration to the gamma ray energy. I don't have a lot of time, so I'm going to have to wave my hands a little bit. I apologize for that. The other thing that LOB has done is that we've done a comprehensive survey of all the starburst galaxies and ultraluminous infrared galaxies that you might hope to see at gamma ray energies. And we're writing up a paper right now and hopefully have that out this spring. And so it's basically a survey of anything that Fermi Lat has seen or anything that has a high star formation rate or is reasonably close. We also do transient work. We follow up on neutrinos. There was a big result in Science about 10 years ago. It was the birth of multi-messenger gamma ray astronomy. And that was a great result. We haven't seen anything since from neutrinos. We do gamma ray burst work. We didn't see the brightest gamma ray burst of all time. Unfortunately, it was right at the full moon. We got on sky, we tried, but it was rough. But we have a lot of limits. There's been 6 GRBs that have been seen. But to give you an idea, we're still catching flares. This is a flare that we caught just a couple months ago. And the highlight here is that this is twice the crab, the double the brightest source of the sky. This thing right up here is about 10 crab at its peak. It's a once a decade event that we just got a few months ago. We're still processing it. Okay, and I will have to move on. So what about beyond vintage VERITAS? What else are we doing? Well, VERITAS is now turning into a bit of an optical astronomy project. We do fast photometry measurements and stellar interferometry. And fast photometry basically means asteroid occultations. So what we've done is we've converted the central pixel in our camera to do millisecond scale photogrammetry. When an asteroid comes across a star, you can measure the light curve. This is a millisecond scale. And what you can see is the diffraction pattern coming on the ingress and the egress of the asteroid coming across. And you can fit this to get a stellar diameter on a milli-arcsecond scale. We've done this 120 times. We have 20 stellar diameters. You can also do something called intensity interferometry, which also gives sub-milli-arcsecond scale. We've created the first catalog in the Northern Hemisphere for this object. These things are way more resolved than, say, Gaia or something like this. But the reason I highlight this is that we're completing an optical upgrade this year, which will allow us to do millisecond scale photometry, not just pointed, but across the entire field of view, which will allow you to catch serendipitous occultations and things like this, where you're talking kilohertz level sampling down to a magnitude limit of about 11.5. Okay, now to CTAO. Okay, well, how has VHE astrophysics evolved in the modern era? Well, we have VERITAS, which came online at Whipple. Almost immediately after starting VERITAS, we started prototyping for the next generation, and finally we have a dual mirror telescope. The thing you notice about this telescope has got a single mirror collecting a camera. Here you have a dual mirror telescope going to a camera. This allows you to reduce the plate scale, getting a more compact camera, better electronics, all these different things. It also allows you to instrument an 8-degree field of view with no aberrations. So we created this, but ultimately with the goal of building CTA, which you see an artist conception right here. This is out in Chile, where you see 4 different classes of telescopes, different sizes to focus on different energy ranges and things like that. And that's going to, roughly come online in 2030. So what is CTAO? Well, it's going to be the world's premier facility. It's a key multi-messenger facility. In January of last year, something called the European Research Infrastructure Consortium was formed. This effectively funded its construction. They got about 350 million euros. It's not quite enough, but good enough for now. It'll detect objects about 100 times faster than VERITAS and give 10 times more resolved pixels. And it's going to have 2 sites, one in the south with scale 50 telescopes, one in the north with scale 13 telescopes. And it's going to come online very, very soon. But the observatory access is limited to investor countries. So I'm going to talk to you about what we're doing to bring the US into this picture. Because 40% of the science right here is reserved for members. Here's anybody can propose to it if you're in the country, and then the host countries get that chunk of time. So where does it stand? Well, prototyping is effectively complete. There's a second science data challenge ongoing. Anybody can really participate. You download the products. If you know how to use Python, you can do it. It's not that hard. The construction is progressing rapidly. You can see there's already 4 large telescopes on the ground in the Canary Islands in the north. In the south, they're putting in the foundations. All of the infrastructure will be complete in the south by the end of this year, and it will have 2 telescopes on the ground. The first science operations will be starting in 2027 with just a partial configuration, just a few telescopes. Yeah, perfect. Okay. And so we expect the north will supersede VERITAS sometime in early 2028. And so what you see then is that we're going to have some scale in both the north and the south that'll get verified in 2028. And we'll start calling for proposals in 2029. And it'll get a little bigger and a little bigger. And then by 2030, we're running full tilt with the alpha configuration. The other bit of news is that the US is investing in CTAO. And I was named the director of the CTAO US program office to sort of manage our membership, our construction commitments, our operations commitments. And we have an application due in April of this year, sort of outlining our vision to get approved. So the CTAO science, I don't have a lot of time to go into detail, but what you can see here are the sensitivity curves. The things that I'll highlight is that it goes from about 300 GeV down to 200 GeV, TeV down to 20 TeV. Okay, you can see the angular resolution. It's a little bit faded out on the screen, but you see about a factor of 1.4 increase. There's a 200-page book which details the science case. There's a really nice website with lots of interactive graphics and videos and things that I recommend people going to. But since this book came out, about 10 years ago, there have been a lot of topical papers with new ideas. Okay, how these key science projects will evolve, given that we're getting fewer telescopes than we initially envisioned. So there's a lot of stuff going on. I'm just going to show a few key points. What is CTAO going to do for sources? What you see here is a simulation of what we expect to see from a galactic plane survey. We're going to detect sources about 100 times faster, and because it has a much larger field of view, you can survey the sky hundreds of times faster, or alternatively go deeper. And so if you run the simulations of what we're planning to do, it shows that our source population is going to grow to more than 1,000. Most of these things are going to be AGN, which really, makes my heart warm, of course. But obviously we have a lot of things along the galactic plane that are quite extended. So what does it do for morphological studies? Well, the angular resolution of CTAO is about an arc minute at high energy, which is the best of any instrument above the X-ray band. It'll allow us to resolve morphological features. This is what SN1006 looks like with the current generation instrumentation. You can see the famous Chandra image up there. This is what it'll look like with CTA. You can actually really start to see the limb features. And this actually allows you to do science beyond making pretty pictures. You can see a simulation of a supernova remnant where it's dominantly leptonic particles creating emission. This is where it's dominantly hadronic particles. You can just see with your eyes, if you can resolve this, you can actually discriminate what is the acceleration mechanisms in these objects based on a morphology and not just spectral studies, which is a new thing for us. Time domain astrophysics. So what you see here is a light curve from Parks 2155 I made as a postdoc now. 20 years ago, that hurts. Okay, this is what it would look like in CTAO. You can see that we have sort of minute scale variations. You know, the dashed line is the brightest source in the sky in that. And what you can see here is that you can start to resolve things on second scales. We're 1,000 times more sensitive than Fermi lat on short time scales. Okay, and we do the projection. It looks like we can extend the horizon where I said we're going redshift 1 out to redshift 2, where the peaks of the AGN and GRB populations are. And we have whole sky visibility, which allows us to see supernova remnants, GRBs, neutrinos, gravitational waves, etc. Okay, what are we doing from the US? Well, one of the things we're doing right away is trying to buy in, have some small scale projects, get us a minimal investment into CTAO so we can be members and participate in the science. So our first contribution is an MRI. It was led by my old PhD advisor in Santa Cruz. We're a part of it. And it's about a $4 million project. It provides $1 million of CTAO equipment. But the idea is we're going to deliver alignment systems for a mid-sized telescopes to CTAO. We've already bought 2 of them. We get 4 more coming. And the other thing we're going to do is we're going to update this prototype telescope's alignment system with this. This does not count towards CTAO construction. So we have $1 million buy. All right, doing some optics work. The next thing we're doing is, this is the cameras now from a small size telescope. So you can see what they look like right there. And what we're doing is we're buying for small size telescopes 6 through 15, so 10 of them, we're buying the electronics modules. So the silicon photomultipliers, the back end electronics, we're fabricating. There's another $4 million project of which $2.5 million, give or take, goes to CTAO equipment. Why is this important? Well, in the early configuration, this will allow them to put 10 more telescopes on site much more quickly, which will increase the sensitivity at around 10 TeV by a factor of 2.5, give or take. So early sensitivity, but it also allows us now to have a $2.5 million investment with the $1 million investment, and now we've bought into CTAO. It also allows us to develop common electronics. These are the same sensors that are used in the CTA telescope at the Whipple Observatory. So we can fully develop them and get things a little better. But really our long-term goal has been called the Schwarzschild-Coudet telescope. Now you recall from back in the early days, I said we image these Cherenkov images. This is what a gamma ray shower looks like. That is what a background shower looks like, quite different. So the better you can resolve these, you can see it with a Hess style telescope, or VERITAS, what you see with this SCT type telescope, you have much finer resolution, which allows you to do everything better. Okay, so that was the goal. We finished a prototype in 2019. This is the optical PSF that we measured across the field of view. It's 4 degrees offset, so really quite far. It's an 8-degree camera, field of view. And you can see that we met our projections, so the optical system works as well, and we managed to detect the brightest source in the sky in a flash observation. So we retired a risk. We know this thing works. We're working to upgrade this thing. We put on a new camera. You can see images from the crane lift, the installation into it. And these are some of the modules that we're testing in Wisconsin over there. Well, eventually we're going to put 11,000 pixels in this camera, give it an 8-degree field of view. And the modules are actually literally shipping right now out to Whipple Observatory. They're somewhere between Wisconsin and Arizona. And we're going to start installing them in April of this year. So we'll get to 11,000 pixels, which is the most pixels ever in a Cherenkov camera. Okay, once we'll do commissioning and science observations in the closing days of the VERITAS project. Okay, what else is going on? About 5 minutes, give or take. So NSF, funded. What is our strategy? 4 of those 5 MRI2 submissions for CTO have been funded by NSF. So the NSF seems to like to give us $4 million chunks of money. Okay. And they strongly encourage us to keep doing this. So that's what we're going to continue to do for now. Okay, we're going to put in SAO is going to put in an MRI submission, probably buying optical alignment systems for these mid-scale telescopes. That first project I saw, will probably buy 17 of those. And the reason they're encouraging us is that the big scale investments at NSF is really uncertain. It's a difficult time. I think we all recognize this. And so they kind of told us not a great time to ask for $40 million, maybe have some patience. It's also a little bit early to propose for an array of these dual mirror telescopes. So we're going to hold on that. We're not done with the prototyping. These are designed for manufacturing assembly, maybe make a Pathfinder, do a CDR. And so that's going to be sort of the scale of a 2028 MRI. And this will ultimately allow us to procure 11 of those dual mirror telescopes as an upgrade to CTAO around about 2030. What does this do for CTAO? Well, we hope to do this. It's endorsed by the decadal survey. And if you do this, you see what the mid-size array down in the south has for sensitivity. This is what it has if you add the dual mirror telescopes to it. This is the upgrade. It gives you 66% more sensitivity, meaning you see things 2 to 3 times faster in $1.5 billion scale observatory. That's a big deal. Okay. It also gives you 40% angular resolution improvement. So that's really where we sell this. And this, remember when I said we go by a factor of 1.4 from VERITAS to CTA, this is that factor over again using these telescopes. This allows you to finish surveys faster, detect smaller, objects and resolve them, and it allows you to do better things with transients. But there's other things we can do. Many of the construction contributions are already defined. What else can we do here? Well, I've been asked by a lot of people about what about a data center? This is not a need. They already have 4. They've told me they only need 3, so they're oversubscribed. Okay, but there are unallocated contributions. They're mostly people. You don't have to know a lot about hardware. You want to jump in and contribute. Just as an example, there's a 20% known shortfall in the software and computing FTEs for CTAO right now. Something that anybody who knows how to program can jump in and help. There's also areas where you can go into calibration and science operations. How do we handle proposals? How do we make proposals go, onto the observing systems? Things like this. There's a lot of areas where we can contribute. And so I'm a little bit over time. So I wanted to kind of come back to things. We have a strong heritage at SAO. It's been about 20 years of the inflationary phase of VHE gamma ray astrophysics, going from 10 iffy sources to now 320 and just climbing faster than I can track. Okay. VERITAS had highly successful operations for almost 20 years. We have 21,000 hours of data, 78 sources, 153 papers, and 88 PhDs. We're likely to operate through summer of next year, and we might have to stop the gamma ray program. Okay, but this could be delayed because of this optical program I alluded to. There's a lot of interest. NSF Astronomy are now starting to attend my project calls, trying to see if they want to do something like this. I've mentioned that we lead the AG at the Starburst Galaxy programs. There's a lot of discoveries. My favorite, of course, is 3C273. Half my career, half my life actually working on it, now that I think about it. We're going to get the first VHE or VERITAS AG catalog submitted this year. And our legacy effort on M82 shows a hadronic origin, and we've done a comprehensive target survey of all the starburst galaxies. So CTAO is going to revolutionize the field. Its funding, its construction has been funded and is moving really rapidly, faster almost than we can really handle it in some sense, We're going to have early science data before 2028, and the early configuration will be done by 2030. We're members. In some sense that we've met the minimum investment. We have to formalize this agreement. That's lawyer stuff. And then, SAO are coordinating the US efforts. And then finally, as a long-term strategy, we're trying to propose a major procurement as an upgrade to the initial thing of CTAO, supplementing these sort of $4 million chunks that we throw in along the way. And I'll leave that for that. I'm just saying there's a lot of places where everybody can contribute, and please come talk to me if you would like to do so.
Thank you so much. It was really exciting. Thanks. Questions?
Yeah, that was a great and exciting talk. Can you review the 10 science categories? I couldn't follow the color code.
There we go. All right. AGN, that's a binary supernova remnant of some flavor. A binary unknown sources. So like things that you don't really know what these things are. You have maybe no emission of X-ray for reasons of electron population, stuff like this. Starburst galaxy. I was trying to do this. It's hard to see where I was at. Yeah, I think that would sort of broad because supernova remnants could be pulsar wind nebula. You have pulsars. You have the shell types and things like that. So there's what VERITAS has is largely AGN. That's what we do is 70% sort of extragalactic. There's not, because the galactic plane doesn't stretch so far up into the north. I mean, it does, but the heart of the galactic stuff is down in the south. And the way this technique works, your threshold and things fall off as you go to larger zenith angles. So there's not a great amount of resolved things that emit up in the north. And so that's why we see with VERITAS fewer of the 10 classes. We have 8, I think it is, than the others. Gamma ray bursts would be another one. It's like pivot. There's a stellar clusters is another one. Sorry, just pivoting. So lots of different science. I specialize in the extragalactic stuff. We call them different subclasses of AGN, something or not. I'm not going to split hairs. We just call them AGN.
Are there any other sources other than 3C273 where you need a different component?
Not right now, no. Now, I mean, we've tried with, Marcus Butcher wrote to me and said, I have this great thing, that I can see and you should look at. And we've tried to look at that. And we have another one that we're trying to look at, but we don't see it. And, the thing is that 3C273 of those is the brightest, right? And it's at 0.2% crab, and forgive me for using crab, but it's a unit that works for me. That 350 hours, that's all you can do, right? I mean, imagine fighting like a 25-hour shot in a single year is a lot. So you try to get to 350 is a bit. It's hard to get there, and so this is why CTAO is so important, because it can just go 3 hours here, 3 hours there, 3 hours here, or even better, 25 hours, right? And really, really drill down. And so, my goal with VERITAS has always been to get the population, identify the high level things, and then allow the population studies people to really hammer it, in 5 or 10 years.
Thanks. It was exciting talk. Thank you. M87, do you monitor M87?
Yes. Yeah. So we've looked at it for at least 15 hours every year since 07. It's flared in 08. It flared in 2010. Maybe a little bit of brightening. Shep made a pretty big deal of it a couple of years back, but it's basically been quiet ever since. So we always time our observations to go with EHT, and so roughly around the full moon in March or April. But yeah, so we look at it this year. We've got 6 hours so far. The campaign is ongoing, and it's low once again. But a graduate student in Dublin, she's writing her thesis. It's a 400-hour exposure, really detailing all of that study. So.
Sorry, so you mentioned that VERITAS, you don't observe all the year. Is CTAO going to have that sort of as well?
So I was on the site committee for CTAO. We really were very purposeful about selecting sites that gave you maximal coverage given the scale of investment. And so the Southern Hemisphere, Iso Paranal in Chile, there's no real issue with that. The Canary Island site on La Palma, they have Kalima issues, and it's not always so wonderful with snow loads in December. But generally speaking, the answer is yes, it should be able to go. Problems with the Arizona site we looked at were, again, the monsoons. There was also a lot of dust loading, and then Mexico was a little, well, as Mexico, we'll leave it at that. And
Now, as with everyone else, great talk. Do you have a non-source catalog published?
yeah, so that's a great question. And so one of the things I've been working on is upper limits effectively, right? And so the AGN catalog at WANA is will have upper limits from the known sources in there, but then there's the things that we looked at and didn't see. And so I have about 250 AGN that I'm working on. The problem is I'm almost embarrassed to say it, I've run out of disk space. I have nearly a petabyte of disk space, and I need more to be able to process the AGN catalog and the limits simultaneously. So the scripts are there. It's just a matter I can't phase the different storage without, and it's not even that much money, but when you're 20 years into a project, you start to run a little short, you know. So we're trying to do this. Once we get the catalog out, we'll clear that disk space and then do the limits. And so we're working on it. Is the right way to say it. And it's literally constrained by hours and, you know, resources at this point. So, but it's, yeah.
So a related question, with all your non-detections, can you do stacking of the sources together?
So we have done that. And so, yeah, so, and with these things, I mean, the thing that you basically come out of this is that, yes, you do start to see an excess when you stack it. You try to subdivide it, like, okay, is it the high peaked objects, things that peak above, say, 10 to the 16th, or the mid or the low peaked objects you look at? And basically what you find is that, okay, the stacked excess starts to come in with high peaked objects that are relatively nearby and almost all the sort of assumptions. And so I haven't found a way to say that, yes, some of these objects that we know we should be looking at probably emit at a low level. And it's hard to figure out which ones we want to throw the 60 hours at. And really, we figured out the one we want to throw 60 hours at, because, you know, if you to detect it at 5 sigma in 60 hours means you see something, give or take, in 10, right? To see something in 100 or 200 means you have to look for 50 hours. And so it's really hard to get to that next step. But that's what the stacking says, is that, yes, you're on the right track, but it doesn't really tell you where to look.
And also, is there a background, like a cosmic background of gamma rays, and can you use the stacking or something like that?
Yes, so if you, I don't have it here, I sometimes show it when I have more time. If you look along this, there's a diffuse emission all along the galactic plane. And it's basically cosmic ray interactions with the gas along the plane, and it tracks very well to that. So that's one of the 10 categories. Going back to it, is this diffuse stuff. And it's actually going to become really difficult when you have CTA, because you now have this diffuse background which you have to model out. It's going to start interfering. And then you have source confusion, where Heinz Folk, who's a good friend of mine, he's probably 90 now. He used to complain that the pulsar wind nebula are like weeds, and they just get in the way of all the interesting sources. And I don't mean to diminish a pulsar wind nebula for the enthusiasts, but we're getting into the era where we're really going to have source confusion of not just the extended sources, but the background as well as the point sources. And I think the galactic center is the classic example where we desperately would love to get dark matter, right, or some signature thereof. And is it one of these supernova remnants there? Is it one of these pulsar wind nebula there? Is it something else? And yeah.
Hey, thank you. Any more questions? No? Okay, if not, let's thank Wystan again. See you next week.
I liked hearing you were doing